Addressing is a key function of network layer protocols that enables data communication between hosts on the same network or on different networks. IPv4 provides hierarchical addressing for packets that carry our data. Designing, implementing, and managing an effective IPv4 addressing plan ensures that our networks can operate effectively and efficiently. Each device on a network must be uniquely identified. At the network layer, we use IP addresses for this identification. Each packet that is sent onto the network is identified with the source and destination addresses of the two end devices. These addresses are 32 bits in length and are carried in the network layer header. For those of us in the human network, a string of 32 bits is difficult to interpret and even more difficult to remember. Therefore, we represent IPv4 addresses using dotted decimal notation. We define a network as a group of hosts that have identical bit patterns in the network portion of their addresses. The host portion identifies one device on that network. If you don't already know the conversion process, learn to convert binary to decimal so you can easily identify the details of an IPv4 address. Within the address range of each IPv4 network, there are three types of addresses. These are network addresses, broadcast addresses, and host addresses. The network address is the Layer 3 method used to identify a group of devices. For example, the network shown in the figure is the 10.0.0.0 network. Devices on the 10.0.0.0 network have identical patterns in the network portion of their addresses. The network address has all zeros in its host portion, as seen here. The IPv4 broadcast address is a special address for each network that enables communication to all the hosts in that network. To send data to all hosts in a network, a host can send a single packet that is addressed to the broadcast address of that network. The broadcast address has all ones in the host portion, as seen here. The broadcast address in this case is 10.0.0.255. Host addresses are used to uniquely identify end devices on a network. Host addresses fill the address space between the network address and the broadcast address. In this example, host addresses range from 10.0.0.1 through 10.0.0.254. In an IPv4 network, hosts can communicate in one of three different ways: unicast, broadcast, and multicast. Unicast transmission is used for the normal host-to-host communication in both a client-server and a peer-to-peer network. Unicast packets use the host address of the destination device as the destination address in the IP packet. Broadcast transmission is used to send packets from a host to all other hosts on a network. In this case, the packet contains a broadcast address as its destination address. When a host receives a packet with the broadcast address as the destination, it processes the packet as it would a packet to its unicast address. A directed broadcast is sent to all hosts on a specific network. The limited broadcast, as seen here, is used for communication with all hosts on the local network. Multicast transmission is designed to conserve bandwidth on networks. It reduces traffic by enabling a host to send a single packet to a selected group of hosts rather than sending multiple unicast transmissions to each host. IPv4 also includes blocks of addresses that are called private addresses. These addresses are designed to be used within an organization and are not used on the Internet. This graphic shows some examples: the 192.168 network, the 10 network, and the 172.16 network. Private addresses are used to extend the life of the IPv4 address space, which has been consumed by the proliferation of IP addressable devices. Privately addressed hosts that wish to communicate over the Internet must have their private addresses translated into public addresses. Network Address Translation, or NAT, is a service that converts private addresses to public addresses and vice versa. NAT is implemented on a device at the edge of the private network, typically a router. One popular example of NAT occurs on a home user's network. Home broadband networks use this service to translate the home network's private addresses into Internet-usable public addresses. Now let's look at a companion to the IP address called the subnet mask. The subnet mask is a 32-bit dotted decimal number that devices use to define the network and host portions of an IP address. Knowing the network portion of an IP address enables devices to make proper packet forwarding decisions. A binary 1 in the subnet mask means that the corresponding bit position in an IP address is part of the network portion. A binary 0 in the subnet mask means that the corresponding bit position in the IP address is part of the host portion. Subnetting is a technique that enables network administrators to create multiple networks from a single network address. In this graphic, the 192.168.1.0 network paired with the 255.255.255.0 subnet mask results in a host portion that supports a single group of 254 host addresses. However, you can use bits from the host portion to create multiple subnets from this single group. Network engineers refer to this as bit borrowing. In this case, the first bit of the original 8-bit host portion is used for subnet creation, which leaves 7 bits for host addresses. The borrowing is indicated by changing the first bit in the last octet of the subnet mask from a 0 to a 1, which results in the new subnet mask of 255.255.255.128. By recalling the definition of the subnet mask, we can see that the first bit of the last octet of the address is now part of the network portion, not the host portion. The result of this subnetting scheme is the transformation of the original single group of 254 addresses into 2 groups of 126 addresses. For each bit borrowed, the number of subnetworks doubles and the number of hosts in each subnet is cut in half. Subnetting is useful for broadcast containment, network organization, and creating security boundaries. Subnetting a subnet, or using variable length subnet masks, enables networkers to maximize addressing efficiency. When identifying the total number of hosts using traditional subnetting, we must allocate the same number of addresses for each subnet. In this example, the /27 mask leads to subnets capable of addressing 30 hosts. If addressing requirements necessitate fixed-size address blocks, such a scheme would be efficient. However, these WAN links only need 2 addresses. Using a /27 mask for WAN links is highly inefficient because only 2 of the 30 available addresses are being used. VLSM enables network engineers to borrow a more appropriate amount of bits to more closely match the number of host addresses needed. In this graphic, you can see that subnet 6 has been further subnetted into 8 additional sub-subnets, each with only 2 host addresses. These small blocks of addresses can be applied to the WAN links that only require 2 host addresses. This method makes sure that host addresses are used more efficiently. This video offers an introductory examination of IP addressing. IPv4 addresses are hierarchical and can represent a complete network, a specific host, or the broadcast address of the network. Network engineers know that careful address planning is required to make the best use of an available addressing space. So get as much experience as possible with IP address allocation and subnetting.